to talk about DC circuits. This is so exciting. Let's do it. Okay, we're going to talk about resistors in series and parallel. EMF, what the heck that is. Kirchhoff's rules, complicated but easy once you learn it. I had a professor say, quantum mechanics is easy, and I was like, you're a jerk, because everything's easy once you get it. DC voltmeters and ammeters, and then null measurements, which is something you don't need to worry about. And then DC circuits containing resistors and capacitors. Okay, so why are we learning all this stuff? So you can be smart. You may never use it, but you never know when one of the relationships you form, you can relate that to something else in your life. You never know, and it happens. Okay, so circuits, they're everywhere around you. These black boxes called phones, what's going on in there? It's magic. Steve Jobs always talked about how these are fancy magic boxes. They're magical. You have no idea how they work. Cause and effect. That's what you're here. That's what you're trying to figure out. So circuits. Tons of circuits in that thing. All it is just current flowing. Some are very simple, like a flashlight, where it's just you put current into it and the light glows and that's it. You get a switch off. So if anybody is interested in designing things, design a lamp, because you can build a circuit and it's just a light bulb. Some circuits, though, are really complicated, like the ones in computers or phones on the chips. You use nanolithography to carve the circuits in. When circuits only contain resistors, and remember a light bulb can be considered a resistor, what we're going to learn applies to DC circuits and AC circuits alike. So it doesn't matter if you're using constant 9 volts or 9 volts AC. What we're about to cover is equally valid for all circuits. We're just considering resistors. Once we start putting capacitors into it, now we have to start doing some math. Okay, so let's not worry about that right this second. Baby steps, because... Okay, the point of circuits is to control the flow of current. Okay, you've got current flow. You want it to go through the light bulb or the heater. You know, let's say you've got a heating element, so you need a ton of current to heat this thing up, but you want a light to click on, letting you know the heater's on. Okay, the light bulb doesn't need a lot of current, so how do you control how much current goes through the heating element and how much goes into the light bulb? That's what we're going to study today. Okay, current turns on a light bulb, unlocks a door when you push a button. Okay, we want to know, how do we control the flow so when we do these things, we get what we want at the end of the day. Knowledge is power, and then we're learning about electricity, so that's important. So resistors, they're a component in a circuit that limits the flow of charge. They resist the flow of charge. The amount of resistance that a resistor has, or the amount that a resistor resists current, is called its resistance. It's a property of the material. There are two ways to combine resistors in a circuit, and that's series and parallel. You can stack resistors up in order or parallelize them, like in parallel circuits. You don't already know what that is, though, so that's what we're learning now. So each of these ways results in different current behaviors. So that's why we differentiate between the two, series and parallel. This is a resistor. In the background, you can see the resistors. They've got this color code that tells you how much resistance the resistor has. It's a labeling thing. It's like a secret club. Those who know how to read color codes and those who don't. And now you're in it, okay? Feels special. This resistor this is how we draw this thing. This is how it looks in real life. This is how it looks in fake life or on paper. It's just a squiggly line, okay? Look at these little guys. These are surface mount, they call it, resistors. They're on the circuit boards that are in your phone, whatever. Over here, these are called through-hole resistors. That's what these are. They're called through-hole because they have these long needles that you just shove into holes. And so those are called through-hole resistors. They're larger, but if you've ever taken a circuit board apart, like maybe when you were a kid you smashed one of your toys before you could regulate your emotions, and maybe some of you still haven't managed to do that. I have trouble sometimes. Don't make me mad. Okay, so you can put resistors in series like this, okay? 1 resistor, 2 resistor, 3 resistor, 4 resistor. This is called series. This is called parallel, where notice the current is coming in from the top here, And now this is like a checkout line at Hy-Vee, where there's always people checking you out, okay? Whereas if you go to Lowe's, there's only one checkout. I don't know how often you go to Lowe's, but it's infuriating. They have like 6 checkout counters and there's only ever one person working. And then someone always asks questions about something that's irrelevant to the cashier. And it's like, what are you doing? Don't talk to them. Just buy something. Okay, go to the customer service if you have a question. That's a life lesson. If any of you do that, stop doing that. Okay, so right now on your sheet, you have an exercise, and I want you to draw resistors, 3 resistors in series and 3 resistors in parallel. So I basically want you to draw this picture and this picture just so you get a sense of what you're doing. Okay, so draw those, pause the video if you need to, and then continue on. So what does it mean for something to be in series? Remember, light bulbs are resistors. So here's 3 light bulbs in series with a battery. So you got your voltage source, and the current has to flow through each component. So this is how it would look on a schematic, and this is how it looks in real life, okay, with resistors or light bulbs or whatever the component may be. Could be a heater, anything. When you're in parallel, here's your circuit, and then the current is split at this, what we call a junction. So we've got a junction here, the current comes in, current goes up, current goes down, and through both resistors, and then recombines at the other end, and then that is parallel. So now the current has to take 2 paths instead of just 1 path. And this is what it looks like in real life. Okay, we've got a switch up here to turn it on and off, to open and close the circuit. Well, you can ignore that for now. But basically you have the positive side of the battery flowing, and then whoop, it gets split into both lights and then recombines back on the other side and then goes to the negative side of the battery. So that's what a parallel circuit looks like. That's what a series circuit looks like. Okay, in series, the current must flow through each resistor sequentially. All right, so if you want to calculate then the total resistance in your circuit, all you have to do is add up each resistor, R1 plus R2 plus R3. Here is your combined circuit schematically. We've got our battery. This might be our 3 light bulbs, R1, R2, and R3. We can imagine then what our total voltage, total current, total resistance is by just adding up the resistors in series. The current through each resistor in series, this is your first point to memorize, is constant. The current flow through R1, R2, R3 is the same. It has to be, because the flow here must continue. You can't have charge flowing and then not flowing in the same tube. You can't have like water flowing really fast in the first half of the hose and then just not flowing anymore. Okay, it's got to go somewhere. Okay, our pipes aren't getting fatter, so there's no Bernoulli's charge equation here. Okay, so the voltage drops at each resistor. This is another important thing. Okay, so we've got the resistances are different, R1, R2, and R3. The current is the same, but the voltages are also different because we have our equation V equals IR. Okay, so if our R's are different and our I's are the same, then V's got to be different because R is different. Okay, so the voltage drops at each resistor. But the sum, this is a key thing, the sum of the voltage drops equals the charge that your battery has. Okay, so the total total voltage then, V total here coming off the battery, let's say it's a 9-volt battery, 9 volts, then this might be 4 volts, this might be 2 volts, 4 plus 2 is 6, so that means this has to have 3 volts across it, because 4 plus 2 plus 3 has to equal our 9 volts. So that's the type of stuff you're going to be doing, is adding up all the resistances, adding up all the voltages, or calculating the voltage across one of these things. Okay, the key thing is that if V total is equal to V1 plus V2 plus V3, then V is equal to IR. This is IR1 plus IR2 plus IR3. And since the current is constant through each of these resistors, you can calculate the voltage drops if you know the resistances, because you just calculate the current, and that's the same for all of them, and then I times R is all you need. Okay, so let's do this example. This is the next problem on your sheet, and I want you to do this problem right now. So suppose the voltage output of your battery is 12 volts, and the resistances are 1 ohm, 6 ohms and 13 ohms. The question is, what's the total resistance? Okay, pause the video, try to calculate that. Unpause. Okay, so what is the total resistance? Our total is just going to be 1 plus 6 plus 13, and all of those have units of ohms. So that's the total resistance, and we've got this example right here. So that should be 20 ohms, okay? So what's the current then through it? So we have that the resistance is 20 ohms, added together. Now what's the current? So the current through this, okay, the first thing we recognize that this is a series circuit, so that means the current going through that circuit is constant. So we know we're starting with a battery of 12 volts and we have a total resistance of 20 ohms. So we've got 12 volts divided by 20 ohms is going to be the total current in our circuit. So if we do 12 divided by 20, then we get 0.60 amps. Okay? Pause. Wait, no, don't pause yet. Pause now. What is the voltage drop across each resistor? Pause. Pause. Okay, we know that the total voltage is 12 volts, and we know that each voltage drop, 1 plus V2 plus V3, has to equal 12 volts, but we also know that the current, I, R1 plus I, R2 plus I, R3, we know the current is 0.6 amps. So if we do 0.6 amps times R1, which is 1 ohm, that's the voltage drop across the first resistor. So that's 0.6 volts, and then so on. And you do that for the other resistors, each of them, okay? And then you create your list of voltage drops. So V1 is equal to 0.6 volts, V2 is equal to 3.6 volts, and V3 is equal to 7.8 volts, okay? Next, what is the power dissipated by each resistor? Okay, so that you can do it P equals IV, P equals I squared R. So we know that the power across the first resistor is I squared times R1. And since the current is constant through each component, we do I squared and then times R1, R2, R3. Remember, power has units of watts. So we get our, do that for each of them, and you get 0.36 watts, 2.16 watts, and 4.68 watts. And then what is the power output of the total source? This is just whatever you got for P1, P2, and P3. The total power, P total, is just P1 plus P2 plus P3. Not W, but P3. Okay, and then that gives you the total power output. Okay, so that's a typical problem you'll have to solve. You'll have to be able to calculate the voltage drop across each resistor, what's the total current in the circuit, what's the voltage total if I give you everything else, you know, that kind of stuff. So next thing, parallel. So that's all series. Parallel. Resistors in parallel. Resistors are in parallel whenever the current must flow through each resistor simultaneously. So we have the current flowing, okay, and it's going through each thing, boom, 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 at the same time, okay? When resistors are in parallel, the current now is different through each resistor. I1, I2, I3 is different. So now we have I1, R1, I2, R2, I3, R3. And V1 is equal to R1, I1, V2 is equal to R2, I2, and V3 is equal to R3, I3. And the beautiful thing about resistors in parallel like this is that the voltage, actually let me do that, the voltage is the same. So that's where it switches. So instead of the current being the same like in series, the current is different in parallel, but the voltage is the same in parallel. So the voltage drop, drop, drop is the same across each of those. And in this case, since we just have one battery and these 3 equal drops, the drop here is equal to the voltage of the battery. So that's how we can, let's say we got a 12 volt battery, we're going to have 12 volts is equal to I1 R1. So if we know what R1 is, we can calculate the current through R1. If we know what R2 is, how many ohms it is, we can calculate the current through that, knowing that that drop is 12 volts. Okay, the other thing is that whatever our total current coming out of the battery is, it has to equal the total current I1 plus I2 plus R3, just because, again, of conservation laws. The voltage drop across each resistor is the same, so V1 and V2 and V3 are equal. So the total current then is just V, since we know V equals IR, V equals IR, therefore I is equal to V over R. Okay, so then we can say that I total is V over R1, V over R2, V over R3, and that's just I1 plus I2 plus I3, and this is how you'd calculate I1 if you wanted to, or just I2, whatever the problem is asking for. So that's it. Between series and parallel, this is the game you're playing. You've got to memorize in which case current is constant, in which case current is changing. So in series versus parallel, and the voltage drops. But that's it. It's these two equations, V equals IR. You just have to learn when is I the same or when is V the same. Okay, so in order to simplify this circuit and treat it as a circuit like that, we can add these resistances together to get the total combined resistance of the circuit, and it's not R1 plus R2 plus R3. It is not that. That is in series. In parallel, it's the reciprocals. Okay, the reciprocal 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus however many resistors you have. Okay, so if we got 3 resistors here, then we do that. Now the thing is, in order to get R total, we have to do, so for example, 1 over R total is equal to 1 over 10 plus 1 over 10. Okay, in order to do that, so that's equal to 2 over 10, right? That's 1 over R total. So then 10 over 2 is equal to R total because we have to take the reverse of that. So we get 5 ohms if these were each 10 ohms. The combined resistance is 5 ohms. Okay, so that's the trick there. You can't just do 1 over R1 plus 1 over R2 plus 1 over R3 and be done. You then have to take 1 over that to undo this reciprocal. So that's a common tricky point that people sometimes overlook. So let's do basically the same thing. We've got 3 resistances. Suppose the voltage output of the battery is 12 volts and the resistances are R1, 1 ohm, 6 ohm, 13 ohm, same circuit that we had, but instead of in series, they're in parallel. And this is the next problem on your sheet. Question is, what is the total resistance? So you're going to do 1 over R total is equal to 1 over 1 plus 1 over 6 plus 1 over 13. Okay, unpause, and you get that the total resistance is about 0.8 ohms. What is the current then in each resistor? Pause, unpause, V equals IR. Okay, R1 and I1. So your voltage, you got 12 volts. You got to calculate what I1 is, I2 and I3. And you get, hopefully, 12 amps, 2 amps, and 0.92 amps. Okay, the more resistance you have, the less the current is going to be through that resistor, so it makes sense that R1 with the lowest resistance is going to have the most current. Okay, so what if you have series and parallel resistors in the same circuit and you want to calculate the total resistance? You have to divide and conquer, and this is going to be a common thing in your homework that you're going to be doing. Is, let's say you got a circuit like this. So you've got your battery, and you've got one resistor, but then it splits. And now this splits off. Oh, we got 3 resistors in parallel. So we need to combine this guy. So 1 over R total there is going to be 1 over R1 plus 1 over R2 plus 1 over R3. And then we solve for what R total is, and that becomes this. Okay? And then we do the same thing here, but it's just 1 over R1 plus 1 over R2, and then that gives us this guy. Wow, these two now are in series, so they just add up. Okay, but these two now are in parallel, so we have to do 1 over R1 plus 1 over R2, whatever this combined resistance is. Once we do that, that becomes 1 resistor. Ooh, now these two are in series, boom, and now we're at the end. Whew, that was fast. Watch that 10 times. And think about that, because that's what you're going to be doing, just adding resistors and simplifying circuits until you get to the end here. And why do you do that? Because then V total equals I total times R total. You can do that on this to figure out the total current going in and out of your circuit, and then you can find currents at individual resistors if you want, using what we just talked about. Okay, so this is another example. What is the total resistance of this circuit? So on your worksheet, I want you to calculate this. You're going to first add this resistor with this resistor in parallel, get a value for that, and then add that to this one in series and get your total resistance of the circuit. So pause that, unpause that, and this is how you do that. You add the first two in parallel, and then you add that to the 1 ohm resistor in series, and you get the total resistance is 5.11 ohms. Okay? Yeah, so after you combine these two, you have your voltage source, and then it looks like this, okay? Because we turned these two resistances into one resistor. Then, redo. Then you can simplify it even further to just that circuit by just adding these two guys together. Okay, so that's how you do that. All right, so moving on to the next section. This is a little bit of a weird thing, and this is only in this section do we, if you see EMF or electromotive force, this is when you have to worry about it, but otherwise, whenever we talk about voltage from a battery, you can just think about the voltage from a battery. So what am I talking about? If you have a battery, let's say 9-volt battery, it's a voltage source, but the battery itself has internal resistance. And you know, whenever there's a resistor, you have a voltage drop. It drops a little bit, the voltage. So EMF, or electromotive force, is basically the rated potential of the battery. So it's not a force, it's a stupid name. It's just the 9 volts. A battery has a 9-volt potential. It's the potential difference if you have no current flowing. But as soon as so it's basically the intrinsic potential of the battery. But as soon as you hook the battery up and current starts flowing, there's a little resistance in the battery itself, which drops its peak potential down a little bit. So instead of 9-volt battery, it's 8.9 volts or something. So let's say you got a 9-volt battery. When you buy it, you hook it up, you measure that it's 9 volts, but as soon as you hook a light bulb to it, it looks like it only has 8.8 volts of potential, and that's because the internal resistance of the battery itself. So we talk about the terminal voltage, which is the voltage that you have. Okay, so you can think of a real battery. This battery here, this is not a picture of things in parallel or whatever. This is just saying that this battery, it's as if there's a resistor hooked to a potential source. Okay, and the total potential that you actually measure is the rated EMF minus the resistance times the current, the internal resistance. Okay, so this is V, this is the rated battery voltage minus the IR, the voltage drop. V equals IR, so this is the IR drop from this internal little resistor. Okay, so the voltage you get out of a battery is the EMF that it's rated minus the IR of its internal resistance. So typical problems are going to be something like you get 11.5 volts off a battery, but there's 12 volts EMF. What is the internal resistance of it? So you'll have to figure out what the current is going through the circuit, and then using that current, you can plug into this equation to solve for the internal resistance of the battery. That's a typical problem. There's a term for the rest of the resistors in the circuit, and that's the load, R load. Okay, so whenever you see R load, that just refers to the rest of the resistors in the circuit. So this is your battery. Okay, it's got 9 volts of source, but then it's imperfect, so it has some resistance. So the voltage you get out of the battery is the EMF minus IR. E could be, let's say, your 9 volts that you expect. IR could be 0.1 volts. That's what your voltage drop from the internal resistance is. So then the actual potential you get to play with is 8.9 volts going to the rest of your circuit. Okay, so most of the time you don't care about this, but only when we specifically talk about it. Okay, otherwise we don't use this equation. So the voltage is just the EMF minus IR. V equals IR. This is the current in your circuit times the resistance, R load of your circuit. And so you get this equation in the book that the EMF then is the current in the circuit times the sum of the resistances, which makes sense because if your internal resistor is in series with the rest of your resistor, then you just add those two together and V equals IR. V equals IR. So here's your battery, here's your internal resistance of the battery. Notice that this internal resistor and the rest of your resistors are in series, so V equals IR, you just do R plus R to get them in series, and then EMF, E, it's just voltage, it's just another voltage, so don't get confused that it's some weird name. It's just V, so you can think of it as the voltage from your battery, and that's the voltage from your battery divided by these two resistors added together. So they're just trying to get you to understand that batteries have an internal resistance. Okay, your next problem you want to calculate, certain battery has a 12 volt EMF, so that means EMF is 12 volts, internal resistance of 0.1 ohms, that's this little r, calculate its terminal voltage, which is what you would measure and what's available to you, V, that's the normal V, when connected to a 10 ohm load. Okay, so you're going to, your EMF then, let me go to this problem. Your EMF then is you got a 12 volt EMF, you divide by your total resistance, and you get 1.188 amps, and then you go to your other equation, V equals EMF minus IR, and then you see that you're available, so that's a 0.1 volt drop or whatever, gives you 11.9 volts here. Okay, so that's all these problems are to determine your terminal voltage. Okay, if you add two batteries together, then the battery is let's say you have two of them, so you got two resistances, then the two resistances just add together and your EMFs just add up, and then the rest of the resistor in your circuit is your R load if it went off to another set of resistors. So this is just like you'd expect. If you have two 2-volt batteries, the total potential is 4 volts, but each of the internal resistances add up, so you got to compensate for that. Most of the time you ignore these internal resistance unless we're really talking about it, so unless I specifically ask you about that, you can just assume you got 9-volt battery. If your batteries are hooked up in opposition to each other, where the plus sides are facing each other, so they're fighting basically, then the EMFs subtract from each other. So E1 minus E2, okay? But the resistances still add up because the resistor is the total resistance in the circuit. So that's the only difference. If you have batteries hooked up or potential sources in opposition, then they subtract from each other. Okay, and that's pretty much it there. That makes sense. Okay, so Kirchhoff's rules. Kirchhoff's first rule is called the junction rule. It means that all the current coming into a junction before it splits off to go parallel, the current going in there has to equal the current leaving that junction. So we'd say that if we call this I1 and this I2 and this I3, then I1 has to equal I2 plus I3. So that's an equation, that's a relationship. All the current coming in has to be accounted for coming out. So this is a way to determine, given how much current goes into a circuit, how much current is through another part of it. You can use that equation. The second rule is called the loop rule, and it says the voltage drops around in a circle have to equal 0. So if you add all the voltage drops up, you need to get back to the beginning. So this is your junction rule. All the current coming in has to be accounted for coming out. So let's say you got 11 amps going into your node, you got 7 amps going here, you gotta have 4 amps going there. So that'll be a typical problem, is we'll give you these two, and then you gotta say, oh, well, there's 4 amps going down there because of this equality. And then you'd have your potential source over here, okay, and then it might loop back like that or something. So you know that this is the positive side of the battery, and so the current would be flowing that way. So that would be the rest of the circuit, for example. The second one, the loop rule, says that all your voltage drops need to add up to 0. So in other words, if your battery has an EMF of 18 volts, that has to, if I start doing voltage drops, that has to equal the 17 volt drop there, the 5 volt drop there, well, that's a 12 volt drop. So we have a, we've got a, from 18 to 17, we've got a 1 volt drop plus a 12 volt drop plus a 5 volt drop. you got 1 plus 12 plus 5, that's 18. So across that resistor is a 1 volt drop, across that resistor is a 12 volt drop, across that resistor is a 5 volt drop. So that's another way to figure out your voltage drops. You can think of it again in terms of height because it's potential. You go up and you start dropping, drop, 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 and you should be back at 0 by the time you get around that loop. Okay, so between those two rules, the junction rule and the loop rule, you can figure out the current and voltage in any single component in a circuit, and that's what you'll have to do by applying these rules, these conservation rules. And we'll have examples of that when we do the sapling. Okay, so there's a special thing here, a nomenclature or a minus sign thing. When a resistor is traversed in the same direction as the current, okay, so let's say you got a resistor and then the current is flowing this way, the drop is minus IR. And you can see that if we go back here, you start with 18 volts and then the drop here is 1 volt. So you start at 18 volts and then minus 1 volts and then minus 12 volts and then minus 5 volts, and that equals 0. So you start with a positive 18 volts and then each subsequent drop is negative. Okay, so and clear these. When you go, so anyway, if you have a circuit like this and then you start going the loop rule like that, as you move, if the current is this way, that's a minus IR. If the current is that way in your loop, then your loop is this way and it's going against the flow of the current, then you do a plus IR. And it just has to do with how you decide to draw your circle, your loop. When an EMF is traversed from minus to plus, the same direction as it moves, then that's your positive, so that's your plus voltage from the battery, and then each one is minus. If you go the opposite direction, now you got to do a minus EMF. So it's just, it makes sense. So you're going around in your loop, okay, that's a minus IR drop. You're going around in your loop, but the current is the opposite direction. That's a plus IR, okay? And then EMF, same thing, you're going around in your loop. That's a plus EMF. You're going around in your loop. That's a minus EMF, okay? So if I look at this problem, this is what you have to do. Then you draw your loop like that and you start going around. So you have plus 18 minus I1 R1 minus I1 R1, a different R1, little R1, big R1, and so on. And you can go around and do that example. Okay, so it's all stamp collecting. Voltmeters, ammeters. There's two important things to learn about these. Voltmeters measure voltage, ammeters measure current. Voltmeters need to be connected in parallel, and ammeters need to be connected in series. Okay, so these are your voltmeters. A volt, if you want to measure the voltage on R1, you hook it in parallel. In R2, hook it in parallel. Across the battery, hook it in parallel. Okay, that's it. Ammeters, this is the key, and this is tricky, that ammeter has to be in the circuit to measure the current. It has to be in the circuit to measure the flow. You have to force the circuit to go through your ammeter. So what that means is you just have to make sure that you hook your ammeter in series, and that's difficult in most circuits because you need to have a special spot where you can break the circuit open and actually insert your current meter. Okay. You can also use special probes that measure the current using the magnetic field, which we'll talk about later. So a galvanometer is another thing that the current goes through a coil of wire, which generates a magnetic field and deflects a needle. The magnetic force is proportional to the current. We're going to learn about this. The force deflects the needle, and then you have a display that tells you how much the voltage is. So you'll do that in lab. Null measurements, when you try to measure voltage, you actually draw some current, so it affects what you're measuring. If you want a really good, precise measurement, what you want to do is balance the voltages in a circuit. So you introduce another voltage into the circuit in order to bring it down to 0. And the whole reason we talk about this in this section is to introduce the thing called a potentiometer, which is a resistor that you can adjust. It's a variable resistor. It slides. And you can get different amounts of it. So we don't care too much about that, but that's just something to be aware of. If you ever get in a lab, do that. Okay, now we'll briefly talk about DC circuits with resistors and capacitors. So remember, AC circuits with resistors and capacitors behave weird, but in a DC circuit, An RC circuit is a circuit with a resistor and a capacitor. They are in series with each other. When you apply a current to the capacitor, it doesn't just immediately kick on, it takes time to charge. It's called, the time it takes to charge is related to something called the time constant. The time constant is the variable tau, and it's literally just the resistance of the resistor times the capacitor, the capacitance of the capacitor. Those two values, that's it. So ohms times farads. The time it takes to charge depends on these two values. So depending on which resistor and capacitor you choose, you get a different time constant, and that allows you to calculate different things. That allows you to have your circuit behave differently. So this is it. You've got a resistor and a capacitor. They are in series. Okay, so you've got your EMF. Notice we're ignoring our internal resistance now because we're not talking about it. So we just have our EMF, and then we have one resistor, and then we've got the current flowing in here, and here's our capacitor, and here's the voltage. Boo. Takes some time to charge. Okay, so your time constant, there's RC, 2 time constants, 3 times constants, 4 times constants, and then you're basically at full charge. Okay. The voltage as a function of time is your original EMF, whatever the battery is, 9 volts, and then 1 minus this exponential function. The exponential function is what makes this graph. Okay, and so it's RC is your time constant, and if you want to know what your voltage is at any time t, you plug in your time in seconds here, and it'll tell you the voltage at that time. Okay, so at t equals 0, e to the 0 is 1, so 1 minus 1 is 1 minus 1 is 0, so you have 0 EMF at t equals 0, and then actually this becomes this number gets smaller and smaller, so it starts at 1 and goes to 0, and then 1 minus that goes up. Okay, so that's how you do that. So you're going to calculate the time constants of RC circuits. This is pretty simple, but once we get into AC circuits, it gets a little bit complicated. Okay, see you guys later. Peace.